researcher at the Australian National University in Canberra. He's served on a variety of expert panels and advisory groups. He was executive director of the International Geosphere Biosphere Program, which is a network of scientists studying global environmental change. So his research spans climate science and Earth system science. And he's been on that interface between that and policy making for nearly 3 decades, which, as you could imagine, could sometimes be a little bit frustrating. So Will is the author of numerous publications on climate science and is a contributing author or reviewer to 5 IPCC reports. So huge welcome, Will, and I'm going to hand it over to you.
And welcome to all of you. I'm coming to you from Ngunnawal Ngambri country, and I'd like to pay my respects to elders past, present, and emerging, and also acknowledge the stewardship that Indigenous people have carried out over this continent for at least 65,000 years. And of course, I'll be talking about how we white fellas have mucked it up in only a century or two. Anyway, so what I'll try to do is unpack the main findings of the IPCC 6th Assessment Report, Working Group 1, which is on the basic science. So I'm going to get some help, I hope, from putting the PowerPoint slides up. I won't try to kill you with PowerPoint. There are only a handful of slides, but I'll try to make the major points through them. Right, so this is based really on the summary for policy makers, which is, I think, an exceptionally clear and well-articulated overview of over 3,000 pages of science. So next slide, please. Just to give you an idea of what actually goes into this, the team of scientists that wrote it, over 200, there were over 14,000 individual papers in the peer-reviewed literature that they had to assess. And they went through some pretty exhaustive rounds. I've been through these myself of expert and government review. And they had to respond to 78,000 technical queries throughout this review process. So it was a pretty exhaustive process. You can be really well assured that the science in this report is absolutely robust and putting on the table just what a challenge we face now. Next slide, please. Well, the first thing people talk about is what's happening to global average temperature. And that's the metric that a lot of people use as a good indicator for the state of the climate system. For now, focus on that right-hand panel, and you can see the black wavy line is the observed change since 1850 when we had reliable records. And you can see over the last half century, since about 1970, an extraordinarily fast increase, accelerating increase in global average temperature. The line, wiggly line sort of in light blue-green at the bottom is what the climate should be doing if we wouldn't be pouring greenhouse gases into it. It should be very stable. So it's very, very clear evidence, unrefutable evidence that climate change is indeed being driven by human emission of greenhouse gases. I'll return to that left-hand panel in just a moment, but let's go on to the next slide, please. Well, just in a capsule, here are the 4 main findings that I would take away from this report. One is the scale and pace at which we are changing the climate system has almost no precedent, and I'll return to that too. It's not just temperature, it's melting ice sheets, acidifying oceans, shifting rainfall zones, rising sea levels. What's happening now is virtually unprecedented in the 4.5 billion year history of Earth. The impacts that we're feeling are not only getting worse, they're actually accelerating. In other words, the rate at which they are occurring is itself increasing. That includes heat waves, both above ground, on land, and under the water, bad fire weather, storms, heavy rainfall, droughts, you name it, they're getting worse. And the thing that we have to be prepared for is even if we get our emissions down deeply over this decade, and I'll talk about that near the end, worsening impacts are already baked in the climate system because of the momentum in the system for about 2 decades. And if we get our act together toward the end of that 2-decade period, we should see the worsening starting to slow down. And the thing that this report really comes out clearly and says for the first time that catastrophic outcomes, collapse of major ice sheets, really rapid temperature increase, and so on, tipping points in the Earth system cannot be ruled out, and they need now to be part of risk assessments. And we hope that governments are paying attention to this because, to me, this is the bottom line. We could have an unlivable planet if we really don't get our act together soon. And that's very clear in this report. Next slide, please. So this is what our temperature rise looks like now on a 2,000-year period. When you look at since 1850, all right, it's sort of pretty steady, and then it goes up reasonably fast. But the last 2,000 years, on that left-hand end there, that's the time of the Roman Empire, so it's a long time ago. But naturally, the climate varies a little bit, a tenth of a degree or so, and you can see that in the lead-up. But that black line on the right-hand side, just hit the next button, please. That's the human influence. And it's extraordinary when you see the size of that influence. It dwarfs any natural variability. In fact, we can go back the entire period of the Holocene, about 12,000 years, and we can't see anything like this. This is quite remarkable. And it's now sitting at 1.2, but rising at an accelerating rate. Next slide, please. So what are these rates of change? This is some information I've put together. You have to really troll through the IPCC to get it, but I've put the references down below. The rate at which we're pouring carbon dioxide, which is the primary greenhouse gas, into the atmosphere, particularly over the last 2 decades since the turn of the century, is about 100 times faster. The maximum rate during the last time the Earth came out of an ice age, and that was a very rapid increase of CO2. So this is, again, just extraordinary. The last half century, our temperature is rising at a rate about 200 times the background rate over the last 7,000 years of the Holocene. That's the epoch where, well, we've just left, and we're now in the Anthropocene. But the past 7,000 years, and in the opposite direction, we had a very, very, very slow cooling trend since 7,000 years ago. But this last one, I think, is really important. This comes out from the Geological Society of London. These rates of change are almost unprecedented in the entire 4.5 billion year geological past. That's the existence of planet Earth. So anytime you look at these statistics that are coming out, these rates of change, from a scientist's point of view, they're just astounding. They're just almost unbelievable. And this is why we are experiencing such a huge increase in extreme events, be they floods, be they massive fires, be they enormous heat waves, all around the planet now. The natural systems simply cannot cope with rates of change this great. Next slide, please. Someone mentioned methane. So this is a little bit of a complicated diagram out of the IPCC report, but it tells you how important methane is. There are 3 panels on this. So starting on the left-hand side, there's one gray bar. That's just a bar graph of how much temperature has risen since the Industrial Revolution. That's sitting at about 1.1. The middle bar with a middle panel with 3 bars shows you the general makeup. The bar in the middle that I have an arrow to is the greenhouse gas temperature rise of about 1.5. But we don't experience 1.5, we experience 1.1. Why is that so? And that's because aerosols, known more popularly as air pollution, in the lower atmosphere scatter some incoming sunlight, so they act to cool the climate. And that's about 0.4 of a degree. So that then, when you take away 0.4 of a degree, gives you the 1.1 that we're seeing. If you go to that big right-hand panel, that's the complicated one. That is breaking down all the factors that humans exert on the climate system. The highest orange bar on the left is carbon dioxide-driven warming. But the next one, and I've got an arrow to that, is warming caused by methane. And that warming over the last decade, these are measured over the last decade, is about 2/3 of that caused by CO2. So although we focus a lot on CO2, and there's a reason for that, because that's a very, very long-lived gas in the atmosphere over many, many millennia. But in the short term, methane is exceptionally important, and it's becoming more important. Well, what's driving those emissions? Well, there are basically 2 primary sectors that do that. One is agriculture, and it comes mainly from cattle production, but also from wet rice production. Those are the 2 major processes in the agricultural sector which emit methane. But increasingly, fossil fuels are increasingly releasing methane to the atmosphere, primarily through a big expansion of the gas industry, where we get fugitive emissions and also leakage, particularly in countries like Russia, which do not have very good infrastructure. And as the gas industry expands, methane emissions are also expanding. Next slide, please. This is a good way of looking at temperature rise. You'll see a lot of graphs that are fairly complicated, but this table is very, very clear. On the left-hand column, we're going down from low emission scenarios. They're called SSPs. That stands for Shared Socioeconomic Pathways. Those are the human drivers. All the way down to the bottom, the SSP 8.5 is the highest emission scenario. But then we have three sets of projections going further into the future. Near term, that's the next couple of decades. Midterm, middle of the century, 2060, and then toward the end of the century. And what that's telling you is the best estimate of what temperature is going to do in those time intervals and the range that the climate models are projecting. But I want to make a couple of points really clearly. This is the baked-in worsening impacts. Look at the left-hand set of columns. That's near term, 2021 to 2040. There is no difference at all from the lowest emission to the highest emission, maybe 1/10 of a degree. That's within the error bars of the models. So that's telling you that we're sitting at 1.1. We already have another 4/10 of a degree baked in to the climate change, to the rise in temperature, which is going to lead to worsening impacts, worsening heat waves, and so on. We simply have to be able to deal with those because there is no way we can avoid them. The midterm also is a bit disconcerting because even the lowest emission scenario now breaches the lower Paris goal of 1.6 degrees. Now we're starting to see a spread from 1.6 up to 2.4 with a high emission scenario. Then if we go long term, then you really see the separation of the scenarios. If we can get our act together and if we learn to remove carbon dioxide from the atmosphere and store it safely, which is built into that low emission scenario, we could reduce temperature to about 1.4. That would be the ideal outcome, the best we could hope for. But if we continue emitting at extremely high rates, we could hit 3 or 4 degrees, which would be disastrous. Next one, please. So I'll just point out some possible outcomes. National pledges now. Countries are making net zero by 2050 pledges and other pledges. If we could meet those, we would be heading somewhere around 2.7 degrees or so, or 3 degrees. So even the pledges we're making now fall far short of what we need to do. Next one, please. Current policies are going to take us to 3 degrees or even more. That is, policies that are currently in place in most countries do not yet reflect the pledges that countries have made. So just trundling along as we are, we could hit 3 degrees or even more by 2100. Next one, please. And if you hit 3 degrees, next one, please. If you hit 3 degrees, there's a real risk that Earth system feedbacks will kick in, and that will take temperature even higher. So basically, this assessment tells us that we really need to do everything we possibly can to meet the Paris climate goals, because the dangerous levels rise exceptionally rapidly once you breach 2 degrees and go higher than that. All right, let's look at Australia now. What is predicted for Australia out to mid-century and is pretty much baked into the system? Well, we're pretty used to heat waves, but they're going to become even more frequent and more intense. And that's both on land, the ones that we humans experience, but also there will be increases in marine heat waves and at the same time ocean acidity. Ocean acidity increases because about 25% of our CO2 emissions are dissolved in the ocean. And that creates carbonic acid, which increases the acidity. Both of these are hammering the Great Barrier Reef. So there is no doubt whatsoever that there will be further mass bleaching events on the reef. And in my view, I think we'll be extremely fortunate to have even remnants of the reef left by 2040 or 2050. It's just a sad reality that we've left things so late that we're going to lose the majority of the reef. Fire weather, we know what that looks like in the east. The intensity, frequency, and duration of this weather is again projected to increase throughout the entire continent over the next decades. Ironically, heavy rainfall will also increase, primarily though across the north. and down a bit into the central, and down the east coast, mainly the northeastern part of Australia. Droughts are going to get worse, mainly across southern Australia and eastern Australia up into southern Queensland. But really hard hit will be the southwest of WA, which is already drying at a rate greater than the southeast. Unfortunately for us, global sea level, which is increasing globally, but our sea levels are rising even faster than the global average around the continent. So that's leading to increasing coastal flooding, shoreline retreat, and so on. That actually is locked in for quite a few centuries. The question is, how fast will it go over the next 300, 400, 500 years? But that's already baked in because of the vast momentum in the ocean. Storms are projected to increase in intensity and frequency throughout much of Australia. So to put it in a nutshell, we've got a tough few decades ahead. We can't avoid that. That's the result of past inaction here and around the rest of the world. So we will have to prepare for these and deal with these. But as I said before, it's absolutely essential that to stop these trends, to slow these trends, and to stabilize them in the second half of the century, we have to act now. We can't wait till 2050 to get going on this. Next slide, please. Okay, now what do we do to meet this challenge? The IPCC will come out with this in its working group 3 assessment report. So I'm taking this from work we've done at the Climate Council. Well, what do we need to do globally? Well, first of all, and I emphasize this as the absolutely most important thing we must do, is that we cannot have any new fossil fuel developments of any kind. That's no coal, no oil, or no gas. So forget about a gas-led recovery. That's just crap. We have to stop all new fossil fuel developments. And then we have to phase out the existing ones as fast as we can. Globally, we need to hit at least a 50% emission reduction by 2030. And that's on a 2005 baseline. But net zero by 2050 is too late. We need to get net zero by 2040 at the latest. And I emphasize here, the real focus needs to be on 2030. That's really the name of the game. If we don't meet this deep emission reduction by 2030, reaching net zero by a decade later won't be possible. At the Climate Council, we reckon we can and we should do better here in Australia, given our enormous renewable resources, technological capability, and the fact that we've actually been a laggard up to now. We have to do some catching up. So for us, just like the rest of the world, no new coal, oil, or gas developments. And again, that means no gas-led recovery. We really should aim for a 75% emission reduction by 2030 on 2005 baseline. That's a huge ask. It's a big challenge, no doubt about it. But we have enormous potential to do this via renewable resources and using those to electrify other sectors of the economy. Technologically, we can do it, but it's going to take an enormous effort and a really rapid and deep change in how we approach the climate challenge here in this country. We should aim for net zero emissions by 2035. And again, that's possible if we really get our act together. But the point I want to make here is whether you look at it here in Australia or look at the challenge globally, the one word that's up there up front is urgency. We've left it so late that to meet the Paris climate goals, there is just no time for dithering anymore. We have to move fast, move decisively, and so on. Next slide, please. Okay, I'm just going to conclude here with a few summaries. This comes from Simon Bradshaw, who's the acting head of research at the Climate Council. He makes 3 really good points. This is the most important update for nearly a decade, and it shows that there is a very narrow and disappearing path to avoiding climate catastrophe. That the only way we'll get onto that path is immediate, deep, and sustained emission reductions. This could be the last warning coming from the IPCC. The next report will be too late. We already know that climate change is having damaging impacts right around the world. And as I mentioned, worse is to come over the next couple of decades. But the decisions we make now, even though we can't affect the extreme events and so on over the next couple of decades, the decisions we make now will be the difference between a longer-term livable future for the young people or a future that is incompatible with well-functioning human societies. And the point we keep hammering is that every choice we make now, every fraction of a degree that we can avoid warming is actually important. It makes a difference in terms of lives, livelihoods, species, ecosystem saved. And if we want to have a future for our children and grandchildren, then strong action now is required. Next slide, please. I'm going to conclude with two comments from my colleague, Joelle Gerges from the ANU. She was one of the lead authors on this AR6, and she wrote a piece in the Saturday paper. A couple of these quotes sum up much better than I could sum up what we face. Our latest report is a terrifying catalog of how climate change is now affecting every continent and ocean on Earth. This last statement I really like. The evening news now looks like a disaster movie. As a climate scientist, I know it's even far worse than that. It's the reality of a rapidly destabilizing world. And the last one, please. Oh, actually, one more after that. Next slide, please. And she writes that during my time working on the sixth assessment report, it dawned on me that this IPCC assessment is the scientific community's last chance to really make a difference. If our latest report and the intensifying evidence now all around us doesn't persuade this generation of political leaders that we must stabilize Earth's climate immediately, then nothing ever will. So the really strong message coming out of this report is this probably is our last really reasonable chance to get the climate system back under some semblance of control. By the time the seventh assessment report comes out, the scientific community is going to say, it's too late, batten down the hatches, you've got to deal with the climate catastrophe. So that's what we face. Last slide, please. And I end my talks with an extremely clear and simple message. When we look at where our planet's going, how we're driving change to the planet, there is no doubt in the scientific community's mind, we are now at the fork of the road. It's not in 2030, it's now. So we have to act now if we want to have a chance of getting this under control. So I'm going to stop there. I'm sure there have been a lot of questions and comments people want to make, and I'm happy to have some discussion now. And thanks to the Get Up crew for helping me with the technology. I'm an old bloke who's not too good with this modern digital technology.
Thank you so much, Will, and thank you for that just really honest and confronting, excellent and clear explanation of the science. We've got a lot of questions, which we won't get through them all, but I just wanted to get to a couple of them. So one of the really highly voted questions is around what are the most impactful changes our government could make to cut climate pollution, just from your perspective?
Yeah, the first one absolutely is to stop expanding the fossil fuel industry. If you don't do that, you're going to lose everything else. So that means the number one thing we need to focus on now is stopping the so-called gas-led recovery, and also stopping the export of coal. I should mention one thing that I'm involved in are a number of court cases where young people are taking action, and we've had some successes, and I've got another 3 or 4 in the works now. So I think anything we can do, whether it's demonstrations, writing to MPs, court cases, we need to stop the expansion of the fossil fuel industry. That has to be done. Anything else, if we don't do that, isn't going to matter. We've got to stop that. So that's what I would focus all our attention on now.
Yeah. And Will, those court cases, we did have a question about legal cases as well. I was wondering if you could speak to how the improving science can actually possibly help with some of those legal cases.
Yeah, I think we are helping with some of those legal cases because most of them are based on future generations. The classic case is probably Sharma versus Minister for Environment. And that was based clearly on the science that we could actually demonstrate that the risk for the future generations of continuing a fossil fuel economy is unacceptable under any moral standards that you want to take. And fortunately, of course, the judge agreed with this approach. And we've stopped some individual fossil fuel developments, not as many as we'd like, but we have on similar grounds that continuing to emit carbon dioxide is going to damage future generations.
Yeah, well, good luck with that. I think that case is now in an appeal stage. Is that right?
Yes, the minister is appealing it. We're waiting to see what form that appeal takes and how we're going to deal with that.
Yeah. So I'll go to another question now. You did touch on this in your presentation, but I think people would be really interested just to have it unpacked a little bit. So it's a question from Tony. So is the 1.5 degree target realistic or simply unachievable now? And how might we think about that?
Look, I think it's unachievable. That's a value judgment on my part, because to achieve it would require enormous emission reductions very fast, and would require us to draw down carbon after mid-century. Because even under the fastest emission scenario that the IPCC put forward there, we breached 1.5. And by the way, those models that do not take into account yet carbon cycle feedbacks like melting permafrost and so on. So our best estimate, building on those models, is not peaking at 1.8, but more 1.6, but more like 1.7 or 1.8. And that takes a lot more drawdown of CO2. So I don't think we're going to make 1.5. However, that narrow pathway that Simon Bradshaw talks about could keep us under 2. And I think that is absolutely essential. And that's still a worthy goal. As we say in the Climate Council, every 1/10 of a degree absolutely does matter in lives saved, ecosystems saved. So we really got to get onto it and make sure we keep it under 2.
Yeah, thank you, Will. And so there are a few questions about removing carbon. Both questions around technologies to remove excess carbon and the potential for that, and questions also around forests and the contribution of forest management, both to the problem and to the solution. So we had questions from Heather and Jill on that, and questions from Rebecca on the technology.
Yeah, okay. Basically, it's called drawing down or drawdown of carbon from the atmosphere. The idea is to pull carbon dioxide out and store it safely. Roughly, there are 2 different approaches. One is a biological approach, because nature knows how to do this. Plants take CO2 up and form through photosynthesis and form carbohydrates and so on. So the idea is to start regrowing forests, drawing down CO2 and so on. But the amount of CO2 you have to draw down if you only use forest is huge. People have done analyses. It starts encroaching on some of the best agricultural land, and it makes it really tough to feed 8 billion people or 9 billion people by 2050. So that's probably not going to work on its own. We need probably technological approaches. That is so-called carbon capture and storage, using industrial processes to capture CO2 out of airstreams, stabilize it, and then compress it, liquefy it, and pump it into used geological formations and cap it. There are a couple of experimental approaches. The most successful one is in Norway, but they're hideously expensive. And again, to expand that to the scale that's required is enormous, and it would be far more costly and dangerous than simply not emitting CO2 in the first place.
Yes, we have noticed the oil and gas lobby pushing that as the new saviour, as if they can continue to expand gas but use carbon capture and storage to simply store it, which does seem quite implausible.
That's right. Well, there is one in Australia, out in Gorgon in WA, in the gas fields there, and that was allowed on the provision they would capture all their CO2 and from the processing and store it, and they haven't been able to do that. It's been too difficult and expensive.
So I've got a question from Wiselaw. I hope I'm pronouncing your name correctly. It's around methane releases from legacy fossil fuel extraction, conversion and transport is becoming a major greenhouse emission that needs to be stopped. How could that be done?
Well, yes, that's absolutely right, and that's a very good point. And again, that gets back to, we just simply have to stop expanding the fossil fuel industry and then phase it out as soon as possible. We're going to have fugitive emissions for the next couple of decades as we phase out. They're just unfortunately built into the system, but we have to slow them down and minimize them and eventually eliminate them by 2030 or 2040.
Great. So we've got a question from Nicholas around sea level rise, and it's asking around how a sea level rise in Australia, perhaps compared to other places. What do we know about that?
Well, it varies. Sea level actually varies around the world, given various topographies, ocean circulation, and so on. So as I noted, our sea level rise tends to be somewhat above the global average. And even around Australia, it varies. The East Coast is a little bit above the global average, but the northern part of Australia is about double the global average. So it depends on where you are. But the point I want to make is that sea level rise is accelerating. It looks like if we don't get our act together, we're in for about a meter of sea level rise as a global average. In a worst case scenario, this is by 2100. In a worst case scenario, it could be 2 meters. But the IPCC make an astounding a warning that, in my view, I would call it astounding that by 2300, you say, well, that's a long way in the future. But if you think just a few generations down the track, a worst case scenario could be 15 meters of sea level rise if we get collapse of ice sheets. That would basically wipe out Australia's economy and much of our infrastructure. So, and they can't rule that out. So we're talking about really, really dangerous impacts. The further you go into the future, that it looks really bad as tipping points like ice sheets collapse, things like this. You simply want to avoid that.
And so you have thought a lot about tipping points, Will. I'm interested in perhaps getting a little bit of perspective on those in terms of the climate science, but maybe also in terms of the politics and the social situation that we are in. What are some of the risks, but also maybe some opportunities?
Well, tipping points are parts of the climate system that when you push them to a certain level, you hit a threshold and they flip to another state, sometimes slowly, sometimes fast. Probably the first tipping point that we're going to cross, and we may be right at it now, is the Arctic sea ice. And that is shrinking during the Northern Hemisphere summer. And as it shrinks, it uncovers more dark ocean water, which enhances the warming, which melts more ice. And you see the feedback mechanism going. But that sits right next to the Greenland ice sheet. And so that as that Arctic sea ice melts, that intensifies the warming in the northern high latitudes. That increases ice loss from Greenland. Greenland starts lowering in elevation as some of that ice loss is from the top. That moves it into a warmer climate, melts even more, and you see that feedback mechanism. That is pouring fresh water onto the Atlantic Ocean and is contributing to a slowdown of the Atlantic circulation system. That is reducing rainfall over the Amazon. And once that hits a critical level, the Amazon burns and we lose the rainforest. That's just a quick overview of some tipping points and how they are connected, and how much of our research now is focusing on tipping cascades and at where are the real danger points. And we think that at now, anytime anything above 2 degrees is rapidly hitting really dangerous territory. And we can't rule out that sometime between 1.5 and 2, you're going to lose some of the most vulnerable tipping points. That's the worst case scenario, is we get a tipping cascade that basically takes climate out of human control. We can get emissions to zero and temperatures just keep going up. You want to avoid that at all costs.
Yeah, for sure. And so can you speak to the opportunities in the other direction? So what are the biggest kind of levers we have to quickly bring pollution down? And I'm curious in that there was some news recently about methane and the opportunity to be certainly stopping the expansion as a point of urgency because of the way it behaves in the atmosphere.
Yeah, look, I think there I would use the term that my colleague Jerry Houston uses, which is silver buckshot, not silver bullets. There are a lot of things and we have to do them simultaneously. Agriculture can be really, really a good positive player here in terms of new farming practices that don't take so much cultivation, better soil management. 2/3 of terrestrial carbon is actually in the soil, not in the plants. Things like biochar are important. So there are many things you can do. Continue to grow food, but with much less carbon emission. Obviously, dietary changes are important. Cattle are an important emitter of methane in particular. And as we go to more vegetarian diets, that could drop as well. A lot of technological things we can do. Obviously, renewables are important. Wind, solar, batteries, pumped hydro. We here in the ACT are 100% renewable now. And we rolled that out in 9 years and under budget. So there are a lot of economic gains now to be had by going renewable. The new future for energy is extremely bright. So there's nothing holding us back except vested interests and political ideologies, and those are important. But we've got to overcome those. And the final comment I would make there is that a very positive idea I want to leave you with is I talk a lot about tipping points. That's my area of research. But there are positive tipping points. There are social tipping points too. And we see it in other aspects in terms of gender issues, in terms of our relationship with our Indigenous colleagues. Things have changed enormously in 10 or 20 years. And they change fast because you cross a social tipping point. I think we can see a tipping point looming on the climate change issue. So anything that people do, even though you think it's small and not important, it actually is important. Tipping points are driven by multiple pressure points. There isn't going to be one big pressure point that's going to solve climate change. It's going to be multiple pressure points all throughout society. So whatever you can do is important, and it'll move us closer to that social tipping point.
Thank you so much, Will. We really, really appreciate your fearless advocacy and your science and the incredibly clear explanations that you've given us tonight. And 100% renewables in 9 years, if ACT can do that, then there's no reason why the rest of the country can't do it at a similarly rapid pace. So I think that's a great note to thank you and wrap up. And I'm going to move on now to